All right, so taking a look at a sapling question that asks us to identify the molecules with polar bonds and the polar molecules. So first, let's look at, so I've drawn out 6 structures here, A, B, C, D, and E, and F. Let's first ask the question, which of them has polar bonds? Polar bonds, right? So that means we're going to look at what periodic trend we're going to be thinking about. Electronegativity, right? So let's look at A. Does A have polar bonds? It has a carbon bond to a chlorine. Is that a polar bond? Yes, so A has polar bonds. Does B have polar bonds? Is a carbon-hydrogen bond polar? No, that's not a very polar bond. Carbon-hydrogen, right, not a very polar bond. But carbon-chlorine bond? It is a polar bond. So A and B both have polar bonds. C, does C have polar bonds? What kind of bonds does C have? It has 2 types of bonds, sigma bonds, but what types of sigma bonds? Carbon-carbon and carbon-hydrogen. Neither of those are polar bonds, right? Carbon-carbon, that's the same thing. Can one side of the carbon be more electronegative than the other? No. About water, OH bonds. Is that a polar bond? Sure is, right? Oxygen is more electronegative than hydrogen. That's going to make that a polar bond. CO2, carbon-oxygen bonds. Are carbon-oxygen, is that a polar bond? Sure is, right? Oxygen is more electronegative, right? Again, looking at those periodic trends. Oxygen and oxygen, is that a polar bond? No, right? Which one's more electronegative, oxygen or oxygen? Oxygen, right? It's not a polar bond. So that's the polar bonds. Now the other part of this question is going to ask us, what are the polar molecules? And that's going to be, we have to think about the whole molecule in 3-dimensional space. Does anybody know what the wedge, this wedge and this hatch mean? The wedge means you're coming out, and the hatch means it's coming away. What's the hybridization state of that carbon? Does it have any pi bonds? No? What's its hybridization state? sp3, right? So it's tetrahedral geometry. Everybody's kind of in their own quadrant, right? Is this molecule polar? No. It's not polar. It has polar bonds, right? Carbon-chlorine bonds are polar. But it has 4 of them, so they're all canceling out. It's all canceled out. Polar bonds, not a polar molecule. So just because you have polar bonds, does that mean you have a polar molecule? No. Good. What about this version? Now there's just 1 chlorine. Is that a polar molecule? Sure is. And actually be a polar molecule if you replace if you had 3 chlorines and 1 hydrogen, it still would be polar. It's that 4th one that fully cancels things out, right? Because they're all the same too. That also matters. Polar bonds, not a polar molecule.
Is that
B. Yep. B has polar bonds, not a polar molecule. No. Polar bonds, polar molecule. That's a polar molecule. Right. That's polar, right? This everything cancels out. This has a polar end. But just because you have polar bonds, does that mean you have a polar molecule? No, it does not mean that. What about C? Is that a polar molecule? No, not at all. Right? Not a polar molecule. What about water? Is water a polar molecule? Yes, absolutely. All right, the area of electron density on the oxygen is more electron rich than the hydrogen. It's a polar molecule. What about CO2? Does CO2 have polar bonds? Are these polar bonds? Yes. Is this a polar molecule? No. It cancels out. What's the hybridization state of that carbon? sp, right? Has 2 pi bonds. What's the geometry for sp hybridized? Linear. So if this is an oxygen pulling to the left and an oxygen pulling to the right, that's a non-polar molecule. It cancels itself out. O2, is that a polar molecule? No, not a polar molecule. All right, so still looking at some polar molecules, seeing if we can identify which of these molecules are polar. So if I label them A, B, C, and D. So A, is A polar? Does A have polar bonds? Sulfur to oxygen? Yeah, it's a polar bond. I consider that a polar bond. Is it a polar molecule?
No.
Why not?
Cancel out.
What do you got right there? Yeah, the lone pair. That's what makes the SO2 different than the CO2. That lone pair creates an area of electron density, so it's not really canceling out like it does in CO2. So that lone pair makes it a polar molecule. So what about C? Is C a polar molecule? They've drawn this poorly on purpose. Is C polar? Maybe if I draw it a different way, maybe it'll change your mind. Now is C polar? Same way, right? These are the same structures. This one's just drawn thinking about the molecules in 3 dimensions, not 2. But see how they did that to try to trick you? Yep. Because the carbon here is what hybridization state? sp3. So what's its bond angles? 0.5. And what's its geometry? Tetrahedral, right? They're drawing it like it's flat. It's not flat. It's tetrahedral. So this is a polar molecule. Trickies. Tricky. Same deal with this D. Again, they're trying to trick you. You see the lone pair, that should give you a hint. But right, this phosphorus is a tetrahedral geometry, so it's also a polar molecule. Right, this is also a polar molecule. All right, so I just drew a couple structures up. Just kind of, actually, I was looking at our class notes from 9/8/17. This is also a figure in the book. It's on bonding and formal charges. I just wanted to show some examples and maybe think about formal charges and what's going on with these and what plus, minus, or neutral. So kind of focus on, I'll circle the atom we want to calculate formal charge for. So we're going to calculate it for carbon, boron, this carbon, nitrogen, and bromine. And I will add in the bromines. I don't want that anymore. I want this. The bromines lone pairs. They're there. If the atoms doesn't have, I've added all the lone pairs I wanted to. So if I haven't put lone pairs in, assume there are no lone pairs there. So take a couple minutes and see if we can figure out the formal charges for all those elements circled. Okay, so let's calculate. Now we've done some work. Let's go ahead and talk about the formal charge here. So what are we going to have for this carbon right here? What's its formal charge? How many bonds does that carbon have? 3. Does it have a lone pair? No. What's its formal charge going to be? Is it electron rich or electron deficient? Deficient. It's going to be a formal plus charge. It's going to be a carbocation, right? It's short some electrons. Yes? Yep. What about the boron? What's the boron? What's its formal charge going to be? Neutral, 0. Right? Boron is in group 3, has 3 valence electrons, so it can only form 3 bonds. What about the carbon with the lone pair and 3 bonds? What's its formal charge going to be? Minus. That's a carbanion. Right, a carbanion. What about this carbon? What's its formal charge going to be? How many bonds does it have? 3 and a lone pair. So it should be negative. Negative. It should be negative. Well, this nitrogen, what's its formal charge going to be? Negative. Nitrogen has 2 bonds and 2 lone pairs. It normally wants 3 bonds and has 1 lone pair, so it has an extra electron, so it has a negative charge. Right? Nitrogen with 2 bonds and a full octet has a negative charge. What about this boron? with 1 bond and 3 lone pairs. What's its formal charge going to be? Neutral, so 0. Good. So there's more examples on that worksheet on your class notes to take a look at, but you kind of start to get a feel for this, right? Remember, I wanted you to think about it, right? There is a formulaic way to do it, which is fine. You can do it that way. But I also want you to be able to look at it and say, oh, that's a carbon with 3 bonds and not a lone pair. That carbon's electron deficient. Right? Be able to look at it and think about how many bonds does it normally want? Is that different? What else is going on? What other factors are in play there? So let's talk about electrons as waves. It's kind of this weird concept of electrons, right? Have this wave particle duality, just like light does, right? Photons and light waves. So electrons are the same way. So a lot of times we draw electrons as little dots, right? And we talk about, moving electrons and have arrows. So that's the thing about electrons as particles. But when we draw molecular orbitals or hybrid orbitals, right? I think the best example is just looking at a p orbital. When you draw a p orbital, you do this weird shading, right? Or maybe a better way to do it is with colors. Right? The problem with shading is people assume when you shade something in, that's where something is. Right? The electron's not there, it's in both these spots. Right? The electron is everywhere. This is the electron. Okay, so that's the electron. Okay, that's weird. But how does that, when we have a bond, right, a covalent bond, we have 2 elements share electrons. So we need their orbitals to overlap to share those electrons, right? We need those orbitals to overlap to share those electrons. So let's go with the colored version. I think it looks cooler. So when electrons are in the same phase, right? In this case, the same color, they're going to interact constructively as waves. Right? So another way to look at this is, let's just draw a wave. Right? And let's say the line I just drew is actually the surface of the water. Right? So there's part of the wave that's above the water, right? There's part of the wave that's below the water. That's what this shading or these colors represent. The red here represents the wave above the water. The blue represents the wave below the water. If 2 waves combine, what happens? You create a bigger wave. That's a constructive interaction. That's a bond. When 2 electrons come together, right? Constructively, that's a bond. It's just the same as 2 waves coming together and making a bigger wave. Now, the alternate is true. All right. What if I have 2 things come together, but they're out of phase? What if I have 2 waves come together and they cancel each other out and completely eliminate the wave? That's called a node, an antibond. Right? So in this case, right, these 2 things, they're out of phase. They're just going to cancel each other out, and that's where we create that node or antibond. So that would make no wave. It would cancel the wave completely out. That'd be a destructive interaction. That'd be not sharing electrons. So another kind of sapling problem is asking us here, label each atom with its optimum CCC bond angle. Note if one or more bond angles are incorrectly placed, a single red X will appear. So you gotta get them all right. So if you get one wrong, let's take it off. So really what this question is asking you though is about bond angles, but what's it really asking you? Do you know the hybridization state of the carbons that I've circled in gray? How are you gonna tell? Carbon gets messy with a plus or minus charge, but if there's no charges, it's pretty clear, right? Then it's all about how many pi bonds you have, right? If there's no plus or minus charge, it's all about how many pi bonds, right? Carbon only gets hard when you have plus and minus charge, but if you just look at the pi bonds, So let's look at this one. How many pi bonds does that carbon have? 2. What hybridization state must it be then? sp. Therefore, right, so sp, box, hybridization state. What's the bond angles for sp? 180. Well, the next one down, what's the hybridization state for that carbon? sp, because it has 2 pi bonds. Because pi bonds are made up of what kind of hybrid orbitals? P orbitals. Yep, there it is. So bond angle for sp is 180 still. What about the next one down? Does it have any pi bonds? Does it have a charge? Not worrying about that. So it's going to be what hybridization state? sp3. That's the hybrid state. What's the bond angle for sp3 hybridized? 109.5. What are the 4 hybrid orbitals for sp3? sp3, 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 and sp3, right? Hybrid orbitals are different than hybridization state. Let's do the next one. What's the hybridization state for that carbon? Does it have any pi bonds? The one I have right here? Does it have any pi bonds? Nope, so it's sp3 again. Next one down. It's a double. I drew that poorly, sorry. It's sp2, hybridized. What are the hybrid orbitals for sp2 hybridized? sp2, 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 p. Right? Always 4. What about the one next down below it? That's also going to be sp2. What's the major bond angle? I would say there's 2 bond angles for sp2 hybridized. What's the major one they always talk about? For sp2 hybridized, the bond angle is 120, but it's important. Why do we forget that 90, right? Where that p orbital is at? That's also important. Remember that bond angle too. So it's 120 and 90. What about right here? How many pi bonds does it have? Does it have any pi bonds? It has 1. If it has 1 pi bond, what hybridization state is it? This one? sp2. The bond angles for sp2 are 120 and 90. Next one, what's the hybridization state for this? sp2. See, it gets a little boring eventually, right? The hybridization state is sp2. The bond angles then are 120 and 90. About that one? sp3. Geometry is what? Tetrahedral. The bond angle is 9.5. Let's talk about resonance. So I have 2 examples of resonance structures. One's a cation, one's something with a plus charge. Another one's an anion, something with a negative charge, carbon with a negative charge. These are the 2 basic examples I showed in class the other day. But just to talk about them again, what's going on here is we're actually spreading out the charge. Remember, we had 4 rules for resonance structures. What were our 4 rules? We said atoms do not change position. Right? Atoms do not change position. We never break sigma bonds. Never break sigma bonds. We only move lone pair electrons or pi bond electrons. And the last one was balance thy charges. Right? Balance your charges. So the first thing I would like to do is number these carbons. 1, 2, 3. 1, 2, 3. So what happened here? We had a pi bond between carbon 2 and 3, and now we have a pi bond between carbon 1 and 2. So the electrons moved. To move electrons, we draw them in, right? 2 electrons in every bond. We're going to lasso those electrons and show them moving to between carbon 1 and 2. I also drew a molecular orbital picture of this, if you remember that, showing all those p orbitals kind of lined up. Okay, let's see if I can do that here quick. I did a picture of one, two, three, and the electrons, right, in that pi bond, the p orbital on carbon 1 was empty, right, because there's a plus charge there. So that gives you that clue about carbocations, what hybridization state they must be in. But what happens here then is these two electrons will move to now be between carbon 1 and 2, forming a new pi bond. Then what p orbital is empty now? On which carbon? Which 3, right? Because if you look, right, 1 and 2 have a new pi bond. 3 is the one that lost the electrons in the bond. One, two, three. Now those electrons are there. And now 3 is the empty p, has the empty orbital. Empty p orbital. Okay? So one thing you hopefully have noticed is, where do we always start arrows? Do arrows start where? What are the superstars of organic chemistry? Electrons. So that's where your arrows should always start, at electron density. Right? You're moving electrons always. You don't move plus charges, right? You move electrons. So in that case, again, let's number some carbons. 1, 2, 3. To go from here to 1 to 2 to 3, what needs to happen to make this happen with this carbanion, now with the carbon with a negative charge? Before, the carbocation, we moved electrons towards it. But now if we have a negative charge, we probably want to use that to move electrons. So where do we need to push electrons towards? Carbon 1 needs to get electron, right? Carbon 1 ends up with a negative charge. We need to push electrons towards carbon 1. So that means we start at 3, we'll lasso those electrons, form a new pi bond between carbon 2 and 3, and the 2 electrons that were in this pi bond now go to carbon 1. That's where those 2 electrons ended up. Carbon with 3 bonds, full octet, meaning it has a lone pair, that is a carbon with a negative charge, right? Yes. So looking at the orbital picture for the carbanion here, 1, 2, 3, notice now, right, this orbital, the p orbital is not empty, it's filled with 2 electrons, right? That's why this has a, right, negative charge. I'm not showing that there's actually, right, there's 2 H's over here. I'm not drawing those in. I didn't do that before. Just showing the p orbitals. So these 2 electrons now are going to move here. And the 2 electrons, right, they're in that pi bond, are going to move as well. So if I take these 2 and go there, I'm going to form a new pi bond between 2 and 3. And then these 2 electrons are going to end up on carbon 1. So what's that look like then? One, 2, 3. All right, so now the electrons move to carbon 1, and that's represented up here between these 2 things. So these electrons are all moving through p orbitals. If you notice that, they're all moving through p orbitals. That should give you a clue about what the hybridization state must be if you want to do resonance. Can you do resonance structures if you're sp3 hybridized? To do a resonance, you need to have p orbitals, right? So if you're sp3 hybridized, you can't do resonance. So that's going to start to tell you something about elements are going to start to choose to be a certain hybrid state if they can do resonance. So get ready. That's coming.